Hi everyone, welcome back to the data science and machine learning track for the afternoon. Next up we have Xavier Boutier, who will be telling us about efficient hyperparameter optimization with Orion. Over to you, Xavier.
Hi, thank you. I'll share my screen. All right. You see it well? I assume you do. Okay, so let's start. Hello, I'm Xavier Boutier. I'm a PhD student and research developer at Mila. Mila is a research institute where researchers are working on machine learning, more specifically deep learning. It's now regrouping, I think, more than 500 researchers, mostly PhD students and professors. And we're developing Orion at Mila now in collaboration with IBM, or a team at IBM since about a year now. The talk will not be specifically about Orion, it's more, let's say, practical approaches or guidelines for efficient hyperparameter optimization, and I'll be presenting this using Orion as an example. But it applies to any other libraries for hyperparameter optimization except for the last part. So I'll be using a short, simple script of scikit-learn as an example throughout the presentation. It doesn't matter if you don't understand all the details here. The important point for the beginning is just that I want to emphasize is what are hyperparameters and why it's important to optimize them. And so at the middle of the script here, we have a line where we instantiate a machine learning algorithm, an SVM for regression, where we pass different values for its configuration. So there's this C and gamma. Doesn't matter what exactly are these hyperparameters for the understanding of the presentation. The only thing is that we need to understand that the hyperparameters, you can think of them as the configuration of your machine learning algorithm. So this is something that you define. It's not something that the algorithm is learning. And there are some default values, right, for the different models in scikit-learn, for instance. And well, you could just use these default values, right? For instance, if we just take the default value for gamma, which is a heuristic called scale, and we apply our model on our data set here is California housing, doesn't matter with the details. And the y-axis is the coefficient, the objective. The way we are measuring the performance of our model is using this coefficient of determination. This is just for the sake of the example, so it doesn't matter if you don't know what coefficient of determination is. All that matters is that we're trying to maximize it, and ideally it should be close to 1, okay? So now if we use these default values, we get an objective that is a bit lower than 0. Is it good? Is it bad? Well, we can try different values of gamma to see if we could get better than that just by changing this specific hyperparameter. And you can see that actually you could get much better performances closer to 1 than by using the default heuristic. There's also other heuristics in the scikit-learn for the SVM, such as the auto scaling of the gamma, which is not really faring better than the scaling one. So you can see that you can get much better performances if you optimize the hyperparameters. And well, maybe the models learn well out of the box with the default values, but if you really want to have the best possible performance out of your model, you should optimize these hyperparameters. So the focus of the talk will be about how can we do this optimization of hyperparameter in a most efficient manner. So first, we'll go to typical steps for the hyperparameter optimization. First, we design the search space. So for gamma, for instance, how do we pick the largest and smallest values of gamma that would be reasonable to try? And then for a second step, we'll choose the algorithm. So how do we want to explore the different values for gamma? Are we going to just do random search, or do we want to do grid search or more fancy algorithms? Then obviously we just run the experiment. So in this presentation, when I say experiment, I mean the full hyperparameter optimization and all the different values for hyperparameters we've tried. This is what I call an experiment. And finally, we look at the results through visualizations. I won't explain here this presentation. I'll come back to it later in the presentation. But yeah, so we look at the results and we try to see if the optimization was good, or if there's something we should try to change and do again the optimization. And so I'll come to a fifth step that is not often discussed. which is the adjustment of the design. So we can think of it as a feedback loop. We look at the results through the visualizations, and we see maybe we did not define the search space properly. Maybe another algorithm would be better. Maybe we realize there are some bugs in the code, and so we adjust the design and we do again the hyperparameter optimization. That will be the last part of the presentation. All right. So first step for search-based design. I use the right part of the slides to just write the code for using Orion for the hyperparameter optimization. So for the first step here, I am defining the search space with just a dictionary with strings representing the name of the hyperparameters. And then here we have a question mark, but that will be a prior that we need to define for the different hyperparameters. So let's say we don't know anything about gamma, and well, maybe the objective is affected by gamma on a linear scale. So we could just say that we will explore different values of gamma on a uniform distribution from some lower bound 0 to some upper bound 100, which doesn't make sense for gamma here, but just for the sake of the example, that would be a prior. And we can see that if we just sample values from this prior, which are represented by the points here, we would have a good coverage of the search space. So there's some good probability that we'll find the optimal value. Here we are optimizing, so maximizing, so looking for the value here. And for many hyperparameters, actually, the objective is affected by the hyperparameter on a logarithmic scale, and often there is some saturation point. So that would be here on the left. There's the logarithmic scale, and then there's a saturation point, and then for all the values of the hyperparameter, it's a very bad objective. I hope you see my cursor because I'm using it a lot to help you understand what I'm saying. All right. So now, if we sample from this uniform distribution from 0 to 1. You'll see that we'll miss most of the good region. Remember, we're maximizing it, and most of the points just fall in the bad region. So it really makes a huge difference if you're using a uniform or a log uniform distribution. Now, if we look at this so this is the same data, I'm just looking at it on the logarithmic scale, we can see more clearly that we missed the good part, just 2 points out of the 50 that fell in the good region that we want to explore. So if we use instead a log uniform distribution, we will have points that are more say uniformly distributed across this logarithmic scale, and there's more chances that we'll find the best values for the hyperparameters to maximize our objective. For some of the hyperparameters, not the case for gamma, but for some of them, they may be discrete. So you can just use this uniform distribution and add discrete equal true. And in this case, you will be sampling points that are on this uniform discrete distribution, so we'll cover it again. It's also the case that for some discrete hyperparameters, they will follow logarithmic scale, or say the objective will be affected on the logarithmic scale. It's the case, for instance, for the size of the hidden layers in an NLP, or the batch size for stochastic gradient descent. So in this case, again, you would want to use a log uniform distribution, now with discrete equal true, so that you're covering well the search space and increasing your chances of finding best hyperparameters. For some hyperparameters, there's some categorical choices. For instance, with gamma, we just discussed about the the real nature of a gamma, but you can also use different heuristics like scale and auto. So you can define this with choices. So you have a list of different choices, and now you're optimizing the different choice. Obviously, with just one hyperparameter, it doesn't make sense to use these choices of 2 values. You could just run it once with scale, once with auto. But if you have many different hyperparameters that you're optimizing at the same time, then you would be trying different values for gamma in combination with the other hyperparameters. Some may be tempted to turn a real hyperparameter, so a real hyperparameter, into categories. Like, for instance, here, gamma just use a list of 0.001, 0.01, and so forth, to make it maybe more concise or more clean. But actually, it's a bad idea, because you don't know what the best values are, because otherwise you would not be doing the hyperparameter optimization, right, in the first place. And when you're defining this list, you may be missing on very good hyperparameters, and just find underperforming model. So I do not recommend turning real hyperparameters into a list of choices. Okay, so let's say for the example, we don't know gamma if it's logarithmic or not, so we'll just use uniform from 10 to the power of -4 to 1. Now we'll start implementing our pipeline for hyperparameterization. So we import the function build experiment, and now we'll be building an experiment. Remember, the experiment, what I mean by that is the full hyperparameterization. And when we are training a model and evaluating the performance, I call this a trial. So we build the experiment, we give a name to the experiment, so that is uniquely identified in the database. Orion is using by default a file system-based database, so you don't need to configure it, but you can read the docs to find the other backend we have. We pass it to space, and then we want to define the algorithm that we'll be using for the experiment. So next part, choosing the right algorithm. Now, to choose the algorithm, there's a couple of different considerations you need to take into account, one of which is the budget you have. So how many set of hyperparameters you're willing to try to find the best ones based on your computational budget, let's say. So actually, before choosing the right algorithm, we'll try to choose the right budget. Just to give you a rough idea, if we look at the search space that has 3 different hyperparameters, the X, Y, and Z, then they're all real. If we make a grid of just 5 points on each dimension, so that's about 125 trials, you can see that it roughly covers the space. So that could be like a starting point. You could think, okay, 5 to the power of number of dimensions is a good starting point for the number of trials, but if you have like 10 or 20 different hyperparameters, it doesn't scale, right? You don't have the budget to train 10,000 trials. So it's only apply in low number of hyperparameters, and then otherwise it's really your computational budget that will determine what is your right budget. But also it's a bit more complicated than that, because it really depends on the surface, so the search-based, its nature. So for instance, if it's fairly smooth, here, this is the objective as a function of the different hyperparameters. If it's fairly smooth, then it's pretty easy to find a good global minima, so you don't need a lot of trials. But if it's very steep, then even this heuristic of just saying, I'll be using 5 to the power of number of dimensions, it would not be enough. You will not find the best hyperparameters using this. So this is really just a very, it's a crude rule of thumb for choosing the budget. Okay, I'll go on now with the choose of the algorithm, and this also is again just general rule of thumbs, but I found it to be useful for researchers around me that are less familiar with hyperparameterization. And I'll present this in the form of a decision tree. So first question is, how many dimensions, how many hyperparameters do you have? If you just have 1 or 2, it's not worth using a very complicated algorithm. You can just use grid search or random search, and that should be good enough. But if you have more than 2 hyperparameters, then, well, first, grid search will not scale well, so you should forget about it. And in some cases, you could still use random search, but there's other algorithms that can be more efficient. So now second question is, what is the computational cost for each of your trials? When you're training your model, does it take less than a minute, or is it more than 5 minutes? If it takes less than 1 minute, then it's quite clear. You just brute force it. You can run many trials, right? So you can just do random search. It's not worth using a complicated algorithm. And if it takes, let's say, more than 5 minutes, then maybe it's worth looking into more complicated algorithms. Okay, so here, this mostly applies for deep learning algorithms. And what I'm saying here is, do you have late learners? So I'll explain what are the algorithms and what are late learners. First, the algorithms here that we consider are hyperbend and ASHA. You can think of them as very aggressive early stopping algorithms. It's not exactly that, but I think it's a good rough idea of what they're doing. And to understand what they're doing, I have this illustration here on the right, where we have the training curves of different neural networks. In this case, I think it was convolutional neural networks, but it doesn't matter. And each blue line here is a training curve, so you can see across the time how the objective is progressing. And how the hyperbend and ASHA are working is that they randomly sample a lot of different set of hyperparameters from the beginning. they train a couple of them up to some certain number of epochs or time, and then they stop all the worst one, and they only let a small fraction of them continue training, and they do it again multiple times until there's just a small fraction that reaches the maximum budget that you allow, let's say 120 epochs. So this is super efficient if you have fairly stable training curves, and also if your training curves are not overlapping too much. What I mean is that if you have curves like that, so I'm calling this red curve here a late learner, it's a set of hyperparameters for which the training is fairly slow, but if you let it training long enough, it will become better than all the other hyperparameters. And so if you're in a setting where you have these late learners, hyperparameter and ASHA will be misled and stop them too early, so you have poor results. An example of a situation where I faced this is when I was using a learning rate schedule, an exponential learning rate schedule. And when I was optimizing the gamma of this exponential learning rate schedule, it was causing me to have these late learners, but they had very good performance. So I wanted them, but hyperparameter and ASHA was stopping them too early, and random search was performing better. So you need to be careful about that. But then if you know, or you're not confident enough that you don't have late learners, you should look into Bayesian optimization, but that will depend on the number of trials you're willing to run. When we're running deep learning algorithms, it's very expensive, so I have not seen so many people run more than 200 trials, in which case you should use Bayesian optimization or a TPE algorithm. But if for some reason you have access to a lot of computational resources and you can run, let's say, up to 1,000 trials, then we're back to, let's say, the second question, and you can just brute force it and use random search. It's not worth using Bayesian optimization in TPE. I would say in practice, with the researchers I collaborate with, I found hyperparameter and ASHA and Bayesian optimization, or TPE, it's a tree structured Parsing estimator. I found them to be the most useful algorithms in most typical scenarios for deep learning. In which case we're training algorithms for a very long time. Okay, so now running the hyperparameter optimization. We had this code here. Now we'll select the algorithm. I'll just use random search to make it simple. I'm copying back the code from the second slide. So we're just fetching the data and separating it into a training and test set and validation set. Now I am encapsulating the instantiation of the model and cross-validation of it into a function that we want to optimize. So we're passing the hyperparameters C and gamma, and we're returning the mean score in a format that is compatible with Orion. Now back to the code for the hyperparameter optimization pipeline. Now I'm just calling experiment.workOn on the main function. And let's say for a total of 200 trials, and I'm fixing the hyperparameter C to 1 because we're just optimizing gamma in this example. I could also use with experiment.tab executor with the Job.the backend. We also support task backend so that we can parallelize the execution for the hyperparameter optimization. Okay, I'll go quickly over the visualization. I'll just have two here, but there's many other ways of visualizing the results. This common one here is called the regret plot. We just see on the x-axis the different trials across time, and on the y-axis the objective. And you can see the different points representing the different set of hyperparameters, and the red line showing the best one we've found so far. So this plot is useful to see how the optimization was going, if we kind of converged or not. In case of random search, not really useful because it's just random, so we just see points scattered all around. Another very useful visualization that I'll be using in the last part is the partial dependency with just one hyperparameter. It's a fairly simple visualization. We just have the different values of the hyperparameter gamma here on the x-axis and objective on the y-axis, and we can see that we've found some optimal region for gamma here. But the partial dependency is really useful when you have multiple hyperparameters, and now you look at all the different combination of pairs of hyperparameters and all the interact for the objective. So here on the diagonal, what we see is, let's say on the bottom right, we see the average objective, the blue curve here, as for the different values of gamma, if we randomly vary all the other hyperparameters. So you can see you can easily observe regions that are optimal for one hyperparameters on this diagonal. And for every possible pairs of hyperparameters, you will have a contour plot like this one, where the color is the objective. So the darker, the worse, the lighter, the better. And you can easily identify dependencies between hyperparameters. So if the objective is a function of two different hyperparameters that are codependent. This is a very useful visualization. And I'll be using this visualization to do iterations of hyperparameterization and adjust our definition of the search space. So last part, we'll be using the experiment version control. So this is something that is specific to Orion. You can think of it as a code version. It's like code version control, but at the level of the experiment. So if you run one time a hyperparameterization, then you stop it. And based on the results, you want to change the search space, or you want to use a different algorithm to do the optimization. And instead of just starting from scratch, you can start again the same experiment. But Orion, instead of corrupting, let's say, this experiment by adding trials that are based on a different search space or a different algorithm, it will branch this experiment, which will be connected to the previous one. And now the child experiment will be able to reuse the data, so the results of the hyperparameters and objective from the parent experiment. And so the experiment version control detect changes on the search space, the algorithm configuration, but also if you're using the command line API, which I'm not covering in this presentation, but you can look at the documentation to learn more about this. If you're using the command line API, Orion is tracking the code version of your script that you're optimizing, if you're versioning it with Git, and also the command line call. So if there's any modification at this level, it will not continue running the same experiment, it will branch to a child one, so that you have a clean separation of the trials using different versions of the code, for instance. So this gives you full traceability, and also it enables you to warm start your algorithm. So quick example here to better explain is, let's say we run one experiment root, and in this one we have gamma equals 0.1, gamma 0.3, gamma 0.6, different trials. And now for some reason we decide to extend the search space, make it larger. So when we run this hyperparameterization, Orion will branch the experiment. Now let's say it's called child 1. And in this one, let's say we have now gamma equals 0.5, gamma 0.8, but the algorithm, let's say we're using Bayesian optimization, it was first fitted using the points coming from the parent experiment. So we can warm start the algorithm. Instead of starting from scratch, we can just continue the experiment since it's just slightly different. So I'll quickly go over an example to show you how this can be done with Orion. We still have the same code than before. The only difference is I added C here, so that it's a bit more interesting. So we have two different hyperparameters we're optimizing. We assume we don't know anything about them, so we'll just be using a uniform distribution for both, which may not be a good thing. And we just run it for 25 trials, just so that we can have just some rough estimate of how the search space looks like. And now we plot the partial dependency with this line here. So first thing that strikes out is the fact that the gamma is really on a logarithmic scale here. And maybe we're missing out small values of gamma that would have been more efficient. So we should change the search space, make it larger to try smaller values of gamma and use it on the logarithmic scale, log uniform. And for C, we cannot really say for now, so we'll just keep C as it is. So we change gamma, now log uniform and a bit smaller, and we train for 50 trials. So since we're using the experiment version control, this will actually just run 25 trials and reuse 25 trials from the parent experiment. We can see that the gamma here, maybe there's an inflection point here, so maybe we found the best values. For C, it's not clear yet, but it seems to be better with larger values. So we'll try larger values. Right, larger than 10, and also it's mostly stable in the large region, and it changes steeply here, so we'll try it on the log uniform as well. So now C log uniform with larger values, and we also try smaller values with gamma. And now max trials 75, so again just 25 trials actually, and reusing 50 trials from the parent experiments. Okay, so now we see that, yeah, it was a good idea to try smaller values for gamma, because we could actually continue increasing a bit improving a bit the objective. And in the case of C, we can see there's the Here the direction goes down, so we should even go further and try larger seeds. And also we see that we're wasting a lot of resources here and here, so we should decrease a bit the search space to avoid searching there again. So now we decrease the value here for the gamma. We're trying just smaller values, and we're increasing the smallest values we try for C. And now max trials for 100. And okay, so that's the last step here. We can see that we found the best values for gamma here. And we can see that for C, actually, we could continue further. I would not have imagined at the beginning that a value of 1,000 would not be the optimal one, and the optimal one would be further down the road, larger values than that. So you can see why it's useful to use these partial dependency to see if the search space you used at the beginning was perhaps too narrow or too large and you're wasting resources. All right, so that's the 5 typical steps for hyperparameter optimization. You design the search space, choose the algorithm, then you run the experiment, you visualize the results, and most importantly, you look at the results to see if you could improve the way you're doing your hyperparameter optimization. And by leveraging the experiment version control, you can avoid wasting resources by starting again from scratch every time. So that's it. I invite you to look at the documentation at orion.readthedocs.io, where you can read about a lot more features on Orion, and it's available on SciPy and Conda, and it's fairly simple to install. Thank you.
That's all. Thank you, Xavier, for a great talk. There's a chance to drop your questions into the Q&A section on the tab on the right, and we can have some time for a few questions here. So Xavier, first question that we have already is, are there any comparisons available between Orion and other hyperparameter optimization solutions like Teapot, AutoML, AutoKeras, and things like that?
Oh yeah, so we have a paper currently under review. So when it will be out, you will have a table with, I think it's 8 other libraries that we compared with. It's really high level comparison. So is there what is the diversity of algorithms that are available? Is it easy to use for the researchers, so it's close to the workflow, or if there's modification to do? Ironically, none of these are in the comparison, Teapot, AutoML, and AutoKeras, because we decided to use more generic hyperparameter optimization frameworks, and these are really for AutoML, where you're optimizing not the hyperparameter, but just trying to find out which kind of algorithm will be the best one to solve a solution. So this is not exactly what Orion is doing. I mean, you could do it with Orion, but it's not exactly what it's meant for.
We have another question asking about when you decide to use Plotly and Matplotlib for your plotting.
Well, in Orion, there's all the visualizations are done with Plotly. We plan to also support Matplotlib, but so far it's not the case. In the presentation, the first visualizations, I guess you recognize the Plotly colors and stuff. So I use Plotly. I use Matplotlib, I mean, for these visualizations. But these were done, I'd say, by hand. But the others were using Orion.
And I have a quick question. You mostly focused on what was going to be most useful for deep learning solutions when you were talking about your rules of thumb for choosing algorithms. And all your examples were more focused on scikit-learn. Does it balance well between the two different problems? I mean, they're quite different problem spaces, and I think there are a lot of users of both. There are a lot of cases for simple models out of scikit-learn. Does Orion work really well with those as well, or is it more targeted towards deep learning?
Well, when you're using, okay, let's focus on algorithms in scikit-learn that are fairly fast and that you would use on a problem where it's fairly fast to fit them, like my example using this VM on a small data set. In this kind of situation, like Bayesian optimization or hyperband or Asha are not useful. You could just do random search, and then the importance about the different libraries is more about how useful they are in making it easier for you to organize your experiments, to parallelize your experiments. And I would say in this case, Orion is doing a fairly good job. But we're more focusing on algorithms for deep learning because this is what researchers are doing at Mila. But yeah, it's funny, the discrepancy between the, the rule of thumbs and my example using scikit-learn. Yeah, so I think the experiment version control could be something that is very useful as well for people that are using more traditional machine learning, like what you would find in scikit-learn.
Yeah. One last quick question: is there anything blocking you putting this on Conda Forge? I think someone would really like a Conda Forge package of this.
I guess not. I mean, it's on Conda yet. It's on Anaconda, but
okay.
Yeah.
All right. Thank you so much. Let's all thank Xavier again, and thanks everyone for joining.
Thank you.